All right, welcome everybody to today's webinar hosted by ISES, the International Solar Energy Society. We are very pleased to have all of you here. My name is Arabella. I am the Communications and Outreach Officer here at the ISES HQ in Freiburg, Germany, and I will be your moderator for today. I am a political scientist and I have joined ISES in 2018 to bring my perspective to the renewable energy transformation. Before we start, I will give you a short introduction into ISES and the work we do, as we have many new participants joining us on this webinar today. The International Solar Energy Society ISES is a non-profit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ISES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. ISES works together with like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ISES, and you can find all of them on our homepage. Some of the benefits are the exclusive access to presentations and webinar recordings such as today's in the ISES webinar archive. ISES members can also get discounts and even free registrations to ISES events and partner events. Every month, ISES publishes a newsletter for our members where you can follow our progress and share your news. Members can also subscribe to our academic journal, Solar Energy, which is our flagship publication at a reduced price. And in the ISES online bookshop, ISES members qualify for reduced prices on the different publications. So we welcome those who are not yet members to join today to support our work. For those who are already a member, we thank you for your support. Now, there's a special offer for everybody attending today's webinar, and that is a 20% discount when joining ISES as a member. All attendees will receive this discount code after the webinar, and you are free to sign up, and the discount code is valid for the next 2 weeks. Now, before we go ahead and start with the webinar, there is a quick introduction, and there's a quick info also. The webinar today will have a Q&A session, which we will have as a cumulative Q&A session at the end of all presentations. And you can submit your questions at any time using the chat box, which you can find on your GoToWebinar panel. So you can simply write in your questions, and then we will go through them in the Q&A session. And with that, I am now happy to introduce our first speaker for today, which is Marc Perez. And I'm especially happy to introduce Marc to you because he played a key role in bringing together all of this webinar today. So Marc is a lead researcher at Clean Power Research in California, and he graduated in Earth and Environmental Engineering as well as Optical Engineering and Physics. At Clean Power Research, he manages science and research in the areas of high penetration solar, solar potential assessment using remote sensing data, and solar forecasting, among others. So now we're going to hear Marc's presentation. Marc, the floor is yours.
Thank you very much, Arabella. And okay, show my screen here and go to full screen mode. Okay, perfect. Well, thank you for the opportunity, everybody. Thank you for joining. I'll be speaking specifically about how do we build a firm renewable power system? How do we achieve high PV penetration and renewables penetration writ large in the global context? And I'll be especially focusing on a case study that we ran recently in the MISO region, which is one of the largest TSOs in the United States, stretching from the Canadian border all the way down to the Gulf of Mexico in the kind of the middle third of the United States. So there are 3 questions that come to mind when we address this question. How do we achieve high penetration renewables? Firstly, are renewables large enough? Secondly, are renewables cheap enough? And thirdly, how do we overcome the intrinsic intermittency inherent in these variable resources like wind and solar? So firstly, are renewables large enough? Well, this sphere represents, the volume of it represents 19 terawatt years per year, unit of energy. It's the global primary energy consumption. And these spheres, the volume of which represents the amount of energy held in the finite resources still remaining in the ground, if we were to extract them at the costs at today's costs. So these are the reasonably assured recoverable reserves from the British Petroleum Statistical Review of World Energy. So this, we extract everything from the ground that's reasonably accessible at current price point, and we burn it or fission it in the case of uranium. And these are the renewables. This is what's accessible every year on planet Earth. Wind, we have about 80 terawatt years. Waves, a subset of wind. 2, we have ocean thermal, we have biomass, hydro, geothermal, tidal, and then we have solar, which is almost 3,000 times the global primary energy demand. And this is only the solar hitting the Earth's continents. And obviously you have conversion efficiency, so that will reduce the size, the effective size of this sphere that's capable of producing energy, but you get the picture. This is every year we receive this much sunlight, and it's order of magnitude larger than if you added up all of the reasonably assured recoverable reserves of the finite resources. So clearly renewables are large enough, even if we only consider wind and solar. And obviously we use PV and wind turbines to extract this energy. Next question, are renewables cheap enough? Here's a recent quote from Fortune magazine that I found interesting in highlighting this point. Solar PV is rapidly becoming the least expensive technology to generate electricity on a pure energy basis. And that's true. This is data from IRENA showing the PV turnkey capital cost for a PV system from 1975 through present day. And as you can see, it decreases exponentially. Back in 1975, we were at around $120,000 per kilowatt, and today we're at less than $1 a watt. And NREL projects even further declines by 2050, but if history is any indication, these will be conservative. So my guess is the price will be even cheaper than this by 2050. So renewables are cheap enough, and it's a similar picture for wind. I just didn't picture it on, I just didn't display it on here. And finally, the most important question of the three is how do we overcome the intrinsic intermittency? Because these resources, while plentiful, aren't always available. So it's a different paradigm from the conventional energy generation scheme where stuff is dispatchable, or is it available 24/7? How do we transform this noisy signal? This is 1 day of solar resource in New York State. And you can see the effect of clouds, intermittent clouds in the middle of the day, into something that's firm and dispatchable, something that can meet load. This is the daily load for the same day in the same region of New York. This is the intraday perspective. And being an intraday perspective, I've highlighted the duck curve here, which you see a lot of, especially in California right now. There's a huge duck being created. This is an intraday imbalance that's very important to consider. Even more importantly, we have the multi-day and seasonal perspective. This is 1 year at the same location of solar resource data. And you can see it's very variable. You know, there are entire periods where we have weather systems come in, multi-day, dropping out the yield for these solar arrays at this location for an extended period of time. How do we transform this noisy signal into something that's available 24/7, 365? How do we move the wind and solar into something more akin to a nuclear power plant, or better yet, something that's more dispatchable than a conventional nuclear power plant? So enter this Minnesota Solar Pathways study. This was a 3-year DOE-funded project to investigate high penetration solar across the state and then the Midwest, and renewables in general. Investigating 100% renewables, we use this CPT model, which is a model we developed that optimizes the portfolio of solutions, including energy storage, geographic dispersion of the generation assets, dispatchable backup, and the hybridization of renewable resources to see how far we can drive down the cost when firmly guaranteeing load 24/7, 365. Solar and wind across these large spatial regions have very different characteristics. Pictured at left here, this is the MISO region. You can see the Gulf of Mexico and Louisiana in the south, and Canada in the north, the Great Lakes. This is the solar capacity factor. Obviously, red is much higher capacity factor in the south, and lots of clouds in the Great Lakes region in the north. For wind, this is the wind capacity factor map. It's quite the opposite. There's a lot more wind power in this, what they call the Saudi Arabia of wind, which is the Dakotas area and Minnesota and this whole region. So they're spatially opposed. How do the expected prices of system components change the picture? As I showed previously, the price of PV and the price of wind is rapidly declining. How does this affect the optimal build out of such a system? Some characteristics regarding MISO: 120 gigawatt peak load, 670 terawatt hours per year. There's 21 gigawatts of wind, considerable. Not much PV so far, less than a gigawatt. Geography can be subdivided into 3 macro regions, north, central, and south, and further subdivided into 10 load resource zones or balancing areas, pictured here at left. The resource is vastly different temporally across these areas, in addition to spatially, the spatial differences. So here is the wind resource for an entire year in blue, 30-day moving average, that's the blue line, versus solar. You can see that the wind moving average is about double the solar. So the capacity factor of wind is much higher, more than double in this region 3, but they're seasonally opposed. There's less wind in the summer than in the winter, and vice versa for the sun. Zone 10, the capacity factor of wind is much lower. So there are no 30-day periods except for a little bit in December where wind is producing more than an equivalent capacity of solar. So that I think is an interesting point, a testament to the strong sunlight in the south. So let's examine the influence these characteristics have on the optimal build out of a fully renewable system. How do we optimize this capacity expansion and dispatch? This CPT model that I mentioned before, which some of my colleagues later on in this session will discuss results of. It optimizes the capacity and dispatch of the following technologies, or it's capable of doing so: wind, PV, and something dispatchable. In this case, I'm going to be speaking about gas, but this could be renewable gas. It could be power to gas or something like that, electrolyzed hydrogen derived. And on the balancing side, we have electricity storage and implicit storage. And by implicit storage, this is a term we've used to coin the concept of overbuilding the capacity of the renewables and curtailment thereof in a smart fashion in order to reduce the need for storage. It's a balancing tool. The optimization is LCOE, levelized cost of electricity, cost-based, and there are 4 cost scenarios that we developed from that latest NREL annual technology baseline: 2050 high and low and 2025 high and low. I won't go over them in detail, but there are capital and operating costs and some technical specs for storage that are important from a modeling perspective. And one thing to remember is 2025 high or 2025 low is the highest cost scenario, and 2050 high is the lowest cost scenario. So it's a semantic difference there. So these 4 scenarios are run for the 14 different geographic zones pictured on the previous page, the 10 load resource zones, 3 regions, and the MISO as a whole. Each region has its own distinct load shape and resource characteristics. All in all, we ran about 25,000 year-long hourly interval dispatch simulations in seeking the optimal across these scenarios. Let's dive in. Let's start the story when the renewables are small enough in capacity never to exceed load in any given hour. So this is the load for a given week in the middle of the summer for zone 7, which is the Michigan oven mitt. You can see that the load peaks in the late afternoon and is a trough in the early morning. Once we increase to 5% PV penetration, there's not a huge impact. We don't really need to change too much. And here the integral of the black is equal to the integral of the yellow, so the integral of the yellow is equal to the integral of the black times P percentage, 5 in this case. We can go to 10%, 15%, 20%, 25%. And this is where we start running into issues because markets are designed to inject renewable power largely with very few constraints. And this works until you reach about 25% energy penetration, at which point you'll start to need energy storage in order to capture the excess and dispatch it when there's a deficit. So this is just, I flipped the script here so you can see the duck curve, same 25% energy penetration. So here we move to 30% and we charge in times of excess, it's green, and we discharge when in times of deficit immediately afterward in pink. We can go to 40%, 50%, 60%, 70%, and we can in fact theoretically go all the way to 100%, and just build the storage large enough to charge during times of excess and discharge at night in times of deficit. This is what the duty cycle looks like. We need about 41 gigawatts of charge capacity and 17 gigawatts of discharge capacity, at least for this week. And I think that's roughly the capacity for the whole year. And this is the state of charge of the storage that will be able to meet the duty cycle that's pictured on the previous page. We need about 4 hours of storage capacity, energy capacity, to mitigate this diurnal variability relative to the PV capacity. So you can see it's discharging at night and charging during the day, discharging at night, charging during the day. This is the intraday perspective. So 100% penetration is possible. The integral of the PV can be set so that we have enough PV, 66 gigawatts in this case, required to meet load on an energy basis, but we're left with a large energy imbalance on a seasonal perspective, summer surpluses and winter shortfalls that are significant. As a result, the state of charge for the entire year, here's a year of storage state of charge, is massive. We need seasonal storage. So we need to discharge all winter and charge all summer. And this is equivalent to about 14 terawatt hours of storage, which is just astronomical. And just to show that from an energy perspective, the seasonal trend is much larger than the diurnal trend, that whole storage state of charge plot where you can see the day-night shift a couple slides ago is all contained within this small black box here. So it's much smaller on an energy basis. And correspondingly, it's exceedingly expensive. We're at roughly $2 per kilowatt hour. This is LCOE on the y-axis here, stacked column, the red portions of which correspond to the contributions of this LCOE that come from storage, and the yellow piece that comes from PV. So you can see the cost is dominated by the need for storage. PV doesn't contribute a lot here. So we can optimize PV overbuild to minimize cost. And the concept here is that in oversizing, we can eliminate these longer term imbalances. So this is what the moving average PV looks like relative to load when we've overbuilt by 2.6x. So that's 2.6 kilowatts of PV for every 1 kilowatt that we need on an energy basis, 174 in this case, gigawatts. And now we're left with a year-round surplus. There are no 30-day periods when the aggregate 174 gigawatts of PV is producing less than load. And correspondingly, the storage size is significantly diminished. Now we only need 4 hours of storage relative to this oversized PV, 719 gigawatt hours instead of almost 14 terawatt hours. And the cost is eliminated. As we start to curtail more and overbuild on the x-axis here, the cost contribution of PV increases because we're overbuilding and we're curtailing, but the cost contribution from storage decreases exponentially, and there's a sweet spot. In this case, for this cost scenario, 2025, low technological development, we're at about 27 cents per kilowatt hour to firmly meet load. And this margin on renewable capacity we're calling implicit storage. And it serves the same balancing effect as you can see here, hence the sweet spot, and it's very economical. So 2025, low technological development, MISO zone 7, 100% PV and storage at 27 cents per kilowatt hour. Let's look at the impact of price. Let's look at 2050 high, which is our lowest cost bracket scenario. So right off the bat, given these cheaper costs for the capital equipment, we see a 70% reduction in LCOE by 2050. We reduce our sweet spot LCOE down to less than 8 cents per kilowatt hour, and that's a testament to the rapidly decreasing cost of PV and a similar but not quite as drastic reduction in the cost of storage. So 2050, high technological development, MISO zone 7, 100% PV and storage at less than 8 cents per kilowatt hour. What about wind? Does the same hold true for wind? So wind, this is again the annual picture for wind, 30-day moving average, and you can see that there are big winter surpluses and big summer shortfalls. So it's the opposite seasonality to PV, at least in this zone. If we can also optimize overbuild, in this case, the optimal happens to be at 2.7 kilowatts of wind relative to the 1 kilowatt we need on an energy basis, and we're left also with a year-round surplus. We eliminate these seasonal imbalances. Correspondingly, the cost also decreases exponentially to a sweet spot of about 6 cents per kilowatt hour. And interestingly, it's around the same optimal curtailment. The sweet spot happens to be as PV. So implicit storage, in this case, the margin on wind capacity saves about almost 90% in LCOE. So 2050 high technological development, MISO Zone 7, 100% wind plus storage at just above 6 cents per kilowatt hour. What about a blend? Can we reduce cost further by hybridizing the resources given that they're seasonally opposed? Let's look at wind plus PV. Yes, indeed, we can decrease the cost down to 4.7 cents per kilowatt hour, in this case, the same cost scenario in the same region, with less curtailment. And we have less curtailment because they're seasonally opposed, so we're mitigating some of the imbalance in that way. So 2050, high technological development, MISO Zone 7, 100% wind, PV, and storage at 4.7 cents per kilowatt hour. What about a larger region? How do the dynamics change here, looking at all of MISO? Well, it's marginally cheaper than Zone 7. If we interconnect all of MISO, 4.2 cents per kilowatt hour, but we have more PV in the optimum wind-solar blend. The blue portions of this stacked area plot are the contributions of the cost from wind, the yellow from PV, the green is the implicit storage overbuilt capacity piece, and the red are the storage components. You can see here the optimal happens to be at 80% PV and 20% wind, and that's because we're capturing a lot higher yield regions in the south. So 2050, high technological development, all of MISO, 100% wind, PV, and storage at 4.2 cents per kilowatt hour. What if we allowed each region to island themselves? How do the costs and wind-solar blends compare in this case? So this is what it looks like. If each load resource zone islanded themselves and optimized their resource blends, the electricity price would be 4.6 cents per kilowatt hour, which is marginally higher than if we leverage the entire MISO interconnect. This is, we cut the core to each of these 10 regions and we build enough capacity within each region to meet the load within each region. The color corresponds to where it landed on the PV wind optimization side of things. There's more wind generally in the north than in the south, but there's only 2 regions where wind is a higher percentage than PV, interestingly, even in Zone 1, which is close to the Saudi Arabia, Dakotas area of the country. So this is the weighted average cost for all of these different regions. And here's where we landed on the wind PV optimization spectrum specifically. So it's slightly more expensive than the MISO as a whole. And this goes to prove that regional resiliency is possible without large-scale interconnection. The color scale is, again, the wind PV blend. And despite the higher wind capacity factor, PV does tend to be dominant. And that's a testament to the price point of PV. It's 30 cents a watt projected turnkey by 2050, which is a stronger reduction than we're expecting from wind, according to NREL. So this is what it looks like when we include a little bit of, when we relax the 100% requirement and allow something like gas, new build gas in this case, to do 5% of the energy. And gas is a stand-in this case, a cost stand-in, an operational stand-in, but it could be any type of dispatchable resource. We're just using the costs from NREL for new build gas, but it doesn't necessarily need to be conventional gas. The black portion is the gas piece, and we reduce our cost further with way less optimal curtailment because gas is standing in and ramping up, or the dispatchable resource is ramping up at times of low yield, requiring less implicit and real storage. So now we come down to 3.5 cents. So this is dispatch with 5% gas. So key takeaways: intrinsic intermittency at ultra-high penetrations can be overcome economically with these optimized technological portfolios, including an optimal wind PV blend, storage both real and implicit. Secondly, large-scale interconnection is cheaper, but not indispensable. Smaller subregions are slightly more expensive than the whole interconnect, but they do provide resiliency benefits and are likely easier to implement. Seasonal storage is certainly not required given the implicit storage concept. And I'd like to leave you with one take home. If there's one take home I could leave you with, it's that 30% wind, 65% solar, 5% gas at 3.5 cents per kilowatt hour. That's not too bad for a region as large as the MISO spatially that serves, that's one of the largest TSOs in the United States. And it's a similar picture that some of my colleagues will talk about in other regions of the world with not too dissimilar prices. So thank you very much.
All right, thank you very much, Marc, for that presentation. Let me take back that screen. Here we go. All right, and then we will be coming to our next speaker, which is Tobias Boström. And I'm going to quickly introduce Tobias to all of you. Tobias, since 2013, he has been a professor in renewable energy at the Arctic University of Norway, and he is a material scientist with an expertise in solar energy who works on system-oriented research. Presently, Tobias' focuses on creating a robust, sustainable energy system by using hybrid renewable energy sources, demand response management, electric transportation, vehicle-to-grid, and other storage solutions. So, Tobias, I hope you're ready. Here comes the screen. And we are looking forward to your presentation.
All right, thank you so much for the presentation. And here is my screen. Can you see the presentation?
Yes, we can. Thank you.
Good. All right, so I've been working with solar energy for the last 20 years. And during the last 50 years, I've been living in Norway. And Norway is the sort of blessed country for EVs. We have a huge EV penetration here. It's because of very, very good subsidies for EVs. So if you look at the new sales of EVs in Norway, it's about 60% presently. And that's, I think, world class. So then it makes sense. It's sort of natural to look at a nationwide PV plus EV energy system. And I got this idea a couple of years ago, and we finally made this calculation. And I'm going to present you some of the findings. So there's a couple of what ifs. What if we could power an entire country on solely PV? Would that be possible? Well, you've seen the presentation from Perez, and the solar energy resource is huge, so it's really not a problem. But there is this issue with intermittency, of course. And Perez talked a lot about that, how you can mitigate the intermittency problem, but it's still there. You need some kind of energy storage. And the idea here in this presentation, in this study, is to look at the EV fleet, electric vehicle fleet, as the energy storage. And what about, well, in order to become sustainable, we have to move away from fossil fuel usage. We cannot continue with that. So, and if you look at the transport sector, already in Norway, we're at 60% new sales, and probably within 10 years, we're going to be having the entire fleet close to 100% electric vehicles. So this is something that's naturally coming, and it's why not use this huge energy reserve that we have? If you look at the aggregated EV capacity, the batteries in each and every one of these cars, you have a huge battery, right? Why not use it? And this is what we're going to look at. Vehicle to grid, well, V2G stands for vehicle to grid. Yeah, this is the explanation. So we have these two what ifs. If we use completely solar and we use EV as energy storage, what can we achieve then? Well, then it could be easily achieve 100% renewable energy system. Well, the word easily is maybe, well, this is up for debate, and this is something I'm going to discuss in the coming next slides. But it should be possible, and this is what we're going to look at. So the objectives of this study was to reveal the potential and the synergy of PV, solar energy plus EVs, electric vehicles. Just looking at those two, nothing else. So this is sort of a conceptual and visionary study to see what the potential and synergy is. And we utilize Spain as a case study. Of course, this is not going to be possible in Norway. Where I live in Tromsø, northern Norway. That's on latitude 70, so that's above the polar circle, and we have no sunlight in the winter, so it's not possible in Norway. But we started looking at where is it possible. If you look at Spain, which is on latitude 40 degrees, we see if it's possible there or not. And the model that we built is a numerical model based on MATLAB. You see it on the right there, but it's not really necessary to look at the different boxes. So the study and the simulation model uses a combination of measured values, simulations, and assumptions. Some of these assumptions should be discussed thoroughly, but I'm going to present the sort of main assumptions. If you look at the EVs, what we've done here in Spain is that we converted all road-going vehicles to electric vehicles. That means cars, buses, lorries, and so on. And on average, these vehicles have about 100 kilowatt hours batteries. So of course, a bus or a lorry needs to have a bigger battery. Cars can have a smaller battery, but on average, it's about 100 kilowatt hours. And on average, these vehicles travel about 50 kilometers per day. So again, lorries and buses travel more and cars travel less, but on average 50 kilometers. And the average energy consumption of these vehicles is about 220 watt hours per kilometer. Again, more for lorries and buses and less for cars. And we implemented this Gaussian curve during the day, that you have the most traveling during the day and least during the night. And then we assume that when the EVs are stationary, they are vehicle to grid connected, meaning that you can charge the cars during the day from PV, from solar energy, and you can discharge them during the night and when it's cloudy. And probably you know this from before, but if you look at your own car in your garage, you probably use it, well, on average, people use it less than 5% of the time. So 95% of the time, your car is stationary. And you have this battery there, and if you take all of these cars together, EVs, you get this huge energy battery reserve that you can utilize. And this is what we're utilizing in this study. If you look at the energy supplied to the system, again, it's purely PV. We're not looking at anything else besides PV. So this is as simple possible system as you can get. And we did look at sort of an average PV production in Spain, taking at least 20 different points and making an aggregated average PV production that we put into the simulation. And if you do that, you have purely PV and you have EVs as the energy storage. What can you achieve? Well, before we go to the EV part, we just want to look at how much PV do we need to supply the energy consumption of Spain, and that's coming in the next slide. So the final energy consumption of Spain is about 960 terawatt hours, and this can be covered by about 56 square meters of PV per capita. And this is quite a simple calculation to arrive at. You don't need any complicated simulation program or anything. It's just something you can calculate on a piece of paper. So the calculation goes, you have 960 terawatt hours of final energy consumption in Spain per year. You have an average PV yield of, in this case, we calculated 365 kilowatt hours per square meter a year. So if you take those numbers, you divide 960 terawatt hours with 365 kilowatt hours, you end up with 2.6 billion square meters of PV. That's what you need in order to supply the load of Spain in terms of PV. And how do we get 56 square meters? Well, simply by looking at the inhabitants of Spain, which is 47 million. So you just divide 2.6 billion by 47 million. You end up at about 50 square meters PV per capita, which really doesn't sound that much. And it's also interesting to compare this number to the built-up area of Spain. So if you look at Spain, the built-up area is about 8.4 billion square meters. And then we see here we need 2.6, so that's about 1/3 of the built-up area of Spain. And why do I compare to built-up? Well, it's kind of interesting to see that PV has many benefits, but one of the benefits is that you can put it in residential areas where you have population, and meaning we don't have to occupy so much space outside our cities and buildings. A lot of these 2.6 billions can be put on already built up area, on facades, on roofs, and so on. So that's quite easy and quite simple to do. Okay, so the issue here is we're disregarding intermittency, which Perez talked a lot about. And so this calculation here is just on 1 year basis, right? You need 56 square meters per capita to provide the final energy consumption per year. So now we need to talk about self-reliance and intermittency. So the self-reliance of the system is a number usually between 0% and 100%. And this is the self-reliance describes to what extent can the supplied energy cover the load. And in this study, we used an hour resolution to look at this self-reliance. So going to, if you take the same result that we got in the previous slide, 56 square meters, but we look at 1 hour resolution, only PV, no EVs. So we just have the PV supplying the energy to cover the load. We get a self-reliance of 37%, which is not very much, but it's quite obvious. I mean, we don't have any sunlight during the night, and when it's cloudy. So we have a self-reliance of 37%. And then the idea comes then, what if we use the EVs as the energy storage to balance the intermittency? So if we put into the system, into the simulation model, that we have all road-going vehicles are EVs, and we're balancing this load with the EVs. So we're storing energy from the sun in the day and releasing energy, feeding into the grid during the night. Then we get a self-reliance of 93%. And that's quite amazing, I think. It's just by having PV plus EVs. We're not adding any extra energy storage. We just use what we have. And again, the road transporting system will become electric pretty soon. So we're just utilizing what we have. In order to get to 100% self-reliance, we can purely increase the PV area per capita to, in this case, we need 73 square meters for Spain to get a self-reliance of 100%. So now we have PV balancing with EV batteries, and then we get 100% self-reliance. I said previously that we were using 100 kilowatt-hour batteries on average for each vehicle. What if we reduce that, which is kind of interesting to see. And here it shows we still get 99.5% self-reliance if the EV battery size is reduced from 100 kilowatt hours to 50 kilowatt hours. So it really doesn't need to be that big in order to do this. And then, of course, we can discuss how we can improve the system, but I'm going to come back to that soon. We did a number of different parameter studies on the simulation model, but these are the most important results that I wanted to bring out. So the conclusion is 100% PV EV, really self-reliant system of Spain is achievable. During the daytime, we use PV directly and store it in the EVs. And during the nighttime, when it's cloudy, we take the energy from the EV batteries using vehicle to grid. And this can be done by having about 70 square meters per capita of PV plus all road-going vehicles, which is about 29 million in Spain, becoming EVs. And that's, I think it's kind of amazing. But of course, there's a number of assumptions here that needs to be discussed. And I'm just going to take those now, and that's sort of further work that we're going to process well, as time goes. We have PhD students working on this, and this was just the first study. So what if we also include wind and hydropower? In the Perez study, we saw that the PV plus wind synergies, and especially if you talk about Norway and Scandinavia, there's huge synergies between wind and hydro and PV. So then we can reduce the number of solar, and also probably we don't need this big EV battery as we've been simulating here. What percentage of EVs is actually needed to get to this 100% self-reliance? But again, in the near future in Norway and probably in many countries, we're going to have 100% EVs fairly soon. And also other questions are, what kind of vehicle to grid connection power is needed? How many connection points do we need to have for this system to work? Preliminary studies shows that it's probably enough with about 10 kilowatts of power per car, which is not that much. But then the fourth question here is probably the most difficult one. What is the social acceptance of this? Would you allow your car to become utilized by the grid company as an energy storage device, which means that your car battery will have more cycling, more wear, more degradation? So in order to do this for the grid company, then you probably need to get reimbursed from the grid company somehow, if they're going to utilize your battery as an energy storage device. So the social acceptance here is really important to address. It should be said that electric vehicle batteries today will outlive the lifetime of the car. They are so good. Of course, you're going to have degradation, but most likely you don't need to change the battery. But if you have much more cycling in terms of vehicle to grid connections, then that could be a question. And what are the cost benefits? So again, the beauty of this system is you don't need any extra energy storage devices. You just have the electric vehicles which are already there as your energy storage device. So the cost of the system should be cheaper than the adding extra types of energy storage. And this is something we're going to look into. And then study these same premises in other countries to see what kind of system is optimal for each country. And yeah, this is what we're going to look into. So the last slide is, this study comes from a scientific journal publication that we just had in February in Smart Energy. So here's the link, you can go into that. And also here's my contact information if you have any questions. But also, yeah, we're looking forward to the questions at the end of this webinar. So thank you so much.
All right, thank you, Tobias. For that, we got quite a bunch of questions already, which I will keep on hand. And then I'm going to take back the screen just quickly and introduce our next speaker to you. And I believe you are seeing his slide now. Our next speaker is Vasilis Pentenakis, and he focuses his research on the interface of energy, water, and the environment. He is founding director of the Center for Life Cycle Analysis at Columbia University, a professor of Earth and Environmental Engineering at Columbia, and he's a distinguished scientist emeritus at Brookhaven National Laboratory. So we are very happy to have you with us today, Vasilis. I'm going to share the screen with you so you can show us your presentation. And for all the speakers, please keep in mind, keep it short, keep it sweet. We do need to mind the time a bit today. All right, here we go.
Thank you for the introduction, Arabella. Good morning, good afternoon, everyone. I'm glad to see about 178 attendees. Can you hear me?
Yes, we can hear you. And yeah, you would have to move up the presentation by a bit. Yeah, there we go. And if you could put it on, yeah, here we are. Perfect.
Let me take actually the menu out of the screen. I hope it does not block the screen because I do have a menu that blocks part of my screen. How is it there?
It doesn't block the screen. We can see it fine.
Okay, great, great. So after those wonderful presentations by Marc and Tobias, on the challenge of variability and intermittency and how it can be addressed with optimizing the grid integration, with overproduction of inexpensive solar electricity, and with smart actually coupling with other renewable energies. I'm going to talk about something kind of more fundamental, about the sustainability of large growth. By large, I'm talking about several hundreds of terawatt hours that would be needed for a clean energy transition. So we all know that photovoltaics is rapidly becoming a major constituent of the power grid mixture in the US and in other countries, China, Europe, and other countries. Now, assessing the sustainability of the rapid growth of photovoltaics necessitates undertaking a very careful analysis, because the photovoltaic markets, I still believe that they are largely enabled by the promise to produce reliable and affordable electricity with minimum environmental burdens. So now, sustainability, in my view, and this is the work that we're doing at Columbia University at the Center for Life Cycle Analysis, it is a transgenerational and global actual issue, and it has three basic dimensions. Low cost, by low cost, I mean affordability in a competitive world, in the industrialized and in the developing world. Resource availability, and there are concerns about some critical materials that are used in several technologies. You can see a list there from tellurium, indium, that are byproducts of the copper and the zinc production, and germanium and silver. And also some people talking about unsustainable, actually large energy use in the manufacturing photovoltaics, which is one of the myths that I'm going to help disperse later. Land use, people are saying that they're using too much land and so on. And the third and the very important dimension that is a special focus in our center is to show that the life cycle impacts and the risk are lower than the alternatives. We have to make comparisons there, because there is not zero risk on anything. So we have to compare with alternatives. So back in 2008, we produced actually a study, a comprehensive study looking at those issues, where we projected that the cost will go down, and then you could have actually enough financial incentives for photovoltaics to become a very, very major technology, and in the United States by 2050 to supply close to 70% of the electricity, 35% of a highly electrified actually society that you use about 10 terawatt hours, 10,000 terawatt hours, double of what we use now. And at that time, we actually projected that the cost of a system will go down to close to $1, about $1.30 per watt, and that electricity could be produced at 6 cents per kilowatt hour without any storage. Now, the industry actually proved that these were very, very, very conservative assumptions. The cost of a system now for large systems is below actually $1, is between 40 and 60 cents, depending on the market. And the cost of solar electricity, at least in the high sun areas, it is something between 4 and 5 cents, or 3 and 5 cents per kilowatt hour. But nevertheless, what we expect to see is what you can see in the curve down that on the left bottom, that is labeled as US renewable electricity generation. We expect really to see, starting from about this year, a very high increase in the penetration of solar. And we project a linear actually increase of the penetration of wind and geothermal and other technologies. But we expect this, what you saw here. And those projections were made in 2007. If those materialize, then the CO2 emissions would be reduced by at least 65% by the year 2050, with reference year 2005. Now, again, the industry actually proved us to be very conservative. You can see the 2007 projections from the Department of Energy, the Solar Energy Technologies Program, that they actually had a target of 6 cents by 2020 for the large utility scale photovoltaic installations. This changed last year because the 2020 targets were actually met early and at a much better level, 4.6 instead of 6. So the new targets now is for 2025, 3 cents, and actually 2030, 2 cents. Those actually numbers, they prove what Tobias and Marc alluded to, that photovoltaics, at least in the high solar areas, they are the cheapest electricity production technology. Now, so we're talking about leading the energy transition, and you can see big actually solar farms like the one in California, 450 megawatt. We have actually up to 750 megawatt in the US, and I think in China we have one giga solar farms, very large ones. We do have a lot of solar on roofs, and this is actually on my home at Dix Hills. It's a 22 years system, 22 years old, still working fine. We have big commercial roofs, and we have actually the #1 in terms of penetration solar electricity technology in China is also solar. So these have taken the price down to what I showed before, and they're expected to take the price down further. Now, what though remains on some people's radar is concerns. It's concerns about electricity, perhaps from solar, that although it becomes cheaper, it can meet other roadblocks. That photovoltaics actually in life cycle, they produce a lot of emissions, that they use a lot of energy, so that the energy return on energy investment is too low, that photovoltaics use too much land, that photovoltaic plants, they could create local heat island effect. This type of concerns by citizens, that many times they delay projects or they block projects. So I'm going to spend the next few minutes addressing those concerns one by one, because they're very important in terms of sustainability. I won't talk more about the affordability. This is proven already. If we have time, I'm going to talk a little bit about the resource availability of materials, but I think it's probably going to wait until the Q&A. So the environmental impact is addressed actually within the life cycle framework. It is a comprehensive framework that it includes all the stages of the production, from taking materials off the ground, and then the different actually processing, refining of the materials, the manufacture of the components that go into the system, from the cells, the modules, the balance of system, the inverters, the cabling, everything and so on, the installation, at the end of the life, decommissioning, there will be some recycling, some will get into the landfills. And for each of these stages, we are actually accounting, quantifying the material inputs, the outputs in terms of materials and emissions, and the energy inputs. And the basic metrics include greenhouse gas emissions, toxic emissions like criteria, pollutants, SO2, NOx, heavy metals, and so on. We accounted for the resource use in terms of materials, water, land, and we do account for the energy payback times. Then for how long the system should operate in order to produce all the energy that has been used in the life cycle, and energy return on investment. So what is the multiple of the energy you get out of a photovoltaic operating at a certain region in comparison to the energy used in all this life cycle? So comparisons here. because there are some emissions in the life cycle of photovoltaics. Why? They don't emit anything while they operate, but the manufacturing, the decommissioning, all of this actually needs energy. So you can see here, and those numbers are better now. Those are older data. They're better because photovoltaics have higher efficiencies than 5 years ago. You can see that the greenhouse gas emissions in photovoltaics, they are lower than those in the nuclear, at least in the United States, and they're about up to 50 times lower than the greenhouse gas emissions in fossil fuel life cycles. Now, with energy return on energy investment, you can still unfortunately see some actually estimates in the literature that they use old numbers, and you can see the big improvement on the energy payback times. Now, if you take in actually radiation of 1700 that is average in Southern Europe, and in the US is a little higher, 2400 kilowatt hours square meter per year will represent a high solar irradiation areas like Southwest, and in actually down in the Atacama Desert and in some other deserts it's much higher. You can see that current estimates is that about a half a year. So for a system that it operates for 25, 30 years, that system pays back the energy that has been used in the life cycle in just a half a year, and the rest 29.5 years will be electricity or energy burden free. But unfortunately, some people actually still recite old numbers, old technologies, and some numbers that they were produced using wrong methodologies. So to correct that, we have connected about 35 analysts in 14 countries, and together we created consensus guidelines of how to go about the life cycle assessment of photovoltaic electricity. That's citing the assumptions, consensus documents. So since then, we have more actually credible analysis by several people, by several analysts in several continents. Now, let's talk a little bit about that myth that photovoltaics uses less land than coal by looking to the historical records of coal use in from coal mining. About 75% of the coal mining in the US is from surface mining. Historical records by Argonne National Laboratory and Oak Ridge National Laboratory, we get this picture that actually photovoltaics use less land. Obviously, you have to account for the land of the mining than coal mining in the United States, less land. And even now, photovoltaics, as they become actually more and more efficient, this picture is becoming better, and the coal mining becomes less and less efficient, and this picture for coal becomes even worse. Now, in addition to actually using land, photovoltaics do not disrupt the land, obviously. And you can see that actually the shade can create some area for pasturing there. And also you can see that underneath and beneath photovoltaics, you can have vegetable gardens. You can have a growth of pollinators here. You can actually have a dual use of land, and let's say vegetable gardens between solar arrays, shading on a parking lot, covering a landfill, on a roof of a commercial building. Oh, I think my time actually, okay, I have to go a little faster. Sorry, Arabella. So something I forgot really to put here is a new path for dual use is floating PV. We have a lot of PV on canals and aqueducts in countries like India. So, and also there are studies that they point out that if you put photovoltaics at the water reservoir of hydroelectric plants, you can get a lot actually out of it with no extra land, just floating PV. It is a new path, a new application, and I just remember about that. So also the industry is very careful in large actually solar farms not to disrupt the land, not to have negative effects or to minimize negative effects on species. I worked closely with US companies, First Solar and SunPower, and I saw how careful they were actually to avoid sensitive areas, minimize impact on ground, maintain and improve vegetation. And we did also at Columbia studies looking at the potential for heat island effect using data from solar farms and 3D simulations. And we saw that there is not any consistent heat island effect. There is actually during the day, there is within the array, there is a temperature increase, but that dissipates very quickly with distance and height, and it completely cools at night. So there is not heat island effect. Another picture that shows actually the dual use and the beauty of it. If you have built-in integrated photovoltaics, you can there actually justify increased cost because they could replace very expensive materials. You have those canopies and so on, and they look beautiful. Some people may not like the gigantic actually structures of wind turbines, but there is not really any visual effect, any negative visual effect on photovoltaics. In my opinion, it is a pleasant actually visual effect on photovoltaics that photovoltaics create on any landscape. And they changes the lives in the developing world, obviously. They enable the kids in Africa actually to read more, the people in Bolivia to have an internet connection, and in Africa to have actually pumping of water and so on, and even desalination. Now, also, photovoltaics still evolve. They can get not only cheaper, but also better. And you can see in a very actually current study that the energy that is used in even the most mature technology in crystalline silicon has been reduced a lot over the last 5 years because of thinner cells and because of higher efficiency cells and because of less kerf loss. And actually we get into kerfless wafers that will reduce the energy even more. And the energy payback times, they become better and better because of higher efficiencies and better material utilization. And also we have new technologies that are coming into the picture, not still in the market, but we have, for example, the promise of perovskites that if they are durable and they last as many years as silicon and cadmium telluride CIGS, they will have much less energy payback times because they use cheaper materials and they're actually faster to develop. So the bottom line is that photovoltaics are great and they are still getting better. Efficiency, cost, new technologies. We haven't invested enough in this technology. So solar energy can sustainably grow to multi-terawatt levels and supply a large fraction of our energy needs if we continue and accelerate the current deployment. And the hope is in the United States, at least, that this is happening now. Now, we didn't have time to talk about this, but I would like actually to connect with the audience through Q&A on the other bullets here. The solar energy is an enabler for resolving the water also and environmental challenges, because you can actually desalinate water if you have affordable and clean energy. And we need, actually, that's another challenge. We're talking about the energy and water and the environmental nexus. Distributed solar enhances grid resiliency. Marc alluding to that. And we don't have time to talk about perhaps a more fair comparison with alternatives would be to account not only the direct cost, but also the benefits of photovoltaics, of solar, of other renewables into the environment. So to include the external environmental and health cost and benefits, this is not accounted in the comparison so far. Thank you, and I'm looking forward to the Q&A.
Thank you very much, Vasilis. Just as I wanted to jump in there, you showed the last slide. Perfect. All right. And so now we move on over to Italy, and we meet Cristina Coronaro. She is Associate Professor of Environmental Technical Physics at the University of Rome Tor Vergata, and she manages the ESTER facility, which consists of solar and weather units, PV modules, monitoring units, and she does research on PV devices of traditional and innovative technologies. So Cristina, I think we would go right ahead to your presentation, please.
Thank you very much, Arabella, for your kind introduction. And I'm going to share my screen. Can you see it?
Yes, we can see it. If you could turn on the full presentation mode, that would be awesome.
Okay.
There we go. Perfect.
We are ready. Thank you for joining. Today I'm talking about an Italian protocol for massive solar penetration. And before starting, I'd like just to introduce our research team. Marco Piero, David Moser, and Matteo Prina from URAC Research in Bolzano, Italy. Richard Perez from the University of Albany in New York. And Marc Perez for Clean Power Research in California. Here is the outline of my talk. I will briefly introduce the Italian energy outlook, since we are talking about Italy and the situation of this country. Then I will just show you the motivation and objective of our research, and then go through the methodology that we used, introducing the flexible PV concept. Already Marc talked about this, and then about the firm PV generation, and we just used this concept to arrive at 100% renewable transition for Italy. Here are some numbers. They are for Italy, they are referred to 2016, since we just used this kind of data for our evaluations. Italy gained the first place as solar producer in the world in that year for PV generation, and the first place for what concern the PV penetration, having almost 8% of PV penetration into the grid. More or less in this here we have the same numbers. For what concern the electricity mix and the story of the renewable share into it, we can see that in 20 years we just passed from 20% of renewable share to almost 35%. And the strategies, the projection of our national energy and climate plan strategy can provide an improvement for this share for 2030 with almost 55%. This means a high improvement in the PV production that is foreseen by the European set plan that drove the PNIEC strategies. And as you can see here, we could pass from almost 24 terawatt-hour per year of PV energy production till 74 terawatt-year in 2030. How much power we need to introduce to get this goal? In 2017, we got 20 gigawatt of PV power installed. We need to arrive at 54 gigawatt in 2030 with an improvement of 170%. So a large amount of PV to reach these goals. But for this improvement, we need to know that PV production has some features, and also Marc and Tobias talk about that, PV production is intermittent. We can have PV during the day and not during the night, and is also variable and difficult to predict due to the weather conditions. We can try to reduce this variability, trying to forecast the PV production into the grid. And this is important because, as already Marc showed, as the penetration of PV grows into the grid, this can produce a dramatic change of the load curve. Here you see the monthly average of the daily profiles of the load and the net load, considering also the PV production for 7% of penetration. As this penetration improves, you can see how this shape is dramatically changed. And this, and if the PV production is not accurately predicted, we can have imbalance into the grid. For this reason, and to reduce this criticism, we suggest a temporal sequence of 3 strategies to allow this massive penetration in Italy. First of all, we improve the forecast accuracy and enlarge the forecast footprint from the current market zones to the whole Italy. Then we use the concept of flexible PV plants to regulate the solar imbalance, trying to get the so-called perfect forecast. And at the end, we would like to use these flexible PV plants to reach the firm PV generation. Here you can see how we can reach all these steps of our strategy. First of all, we talk about forecast accuracy. Here you can see Italy as divided in the 6 market zones, and the current TSO for Italy make forecast for the PV injection into the grid at market zone level. And for the year 2016, they got an imbalance. That means a difference between the production and the forecast of almost 17 terawatt-hour. If we try to improve this forecast, and we try to do this with our algorithm at the market zone level, we got a reduction of imbalance of almost 13%. But if we also enlarge the footprint, extending our forecast to all Italy, this reduction goes to 27%. So we can really do something with improving the PV forecast. Then what we can implement is the flexible PV plant concept. And here you can see an example of a forecast of PV production for a nice day. And for the same day, we will have a PV output, so a real PV production that usually would be different from the forecast. Here we have a underproduction during the first part of the day and an overproduction during the second part of the day. What we want to do is try to guarantee the what was forecasted in a way that we will reduce the imbalance between what is expected and what is really produced. And how we can do this? We can do this just introducing some batteries that can add energy in the first part of the day to reach what predicted, or we can add solar oversupply and curtailment and cut the exceeded power during the second part of the day. In this way, we just guarantee what was predicted. Here you can see how this concept can be applied to regulate the solar imbalance and to arrive at the perfect forecast concept. Here we have the 2016 situation and the difference between the current production and the forecast production. As you can see, there is an error between these two sets of data. If we apply the PV, the flexible PV concept, introducing some batteries and cutting almost 4% of PV generation, what we can do is halve the forecast error. Since we completely remove what is the overproduction, and we slightly reduce because the batteries are not a very large amount, the underproduction. At this stage, if we improve the amount of batteries, keeping the same amount of curtailment, we can reach what we call the perfect forecast. So we will have the perfect match between the forecast and what is really injected into the grid. But we can push further this concept, trying to match what is the shape of the PV production with the load shape, and this can be done optimally balancing the presence of batteries and solar oversupply and curtailment, as Marc already said. And in this way, we have the matching perfect match, and so the firm PV generation. This concept can be introduced when the large scale PV plants and the battery will reach a price that would be economically attractive. And in our study, we consider the year 2060 as the year in which this concept will be feasible. So we made optimal balancing between solar and wind overbuilt and curtailment and storage, minimizing the LCOE, varying the PV and wind curtailment. And so from this graph, very similar to the one that Marc showed for the MISO system, we could find a minimum which represent the optimal balancing between all these actors that work together into the systems. And this can be done for example, in this case, with 130 gigawatt of PV and 120 gigawatt hour of batteries. So considering this final strategy, we can trace a scenario that can move from the dump PV, which is the actual PV installed, to the PV imbalance regulation and PV perfect forecast that can bring to reach what is the goal of the PNEC that I showed you before, and then go to the transition to the firm PV in 2060. And all this scenario can be done minimizing the cost and keeping the cost below the minimum national price for energy that is in 2016 was fixed at almost 43 euro over megawatt hour. But we need quite a large amount of PV, 130 gigawatt, and that we need to install somewhere. Here I can show you, just for example, the monthly average of the daily profiles, considering 13% of wind solar penetration in 2016, with a large amount of fossil fuel and natural gas to match what is the load. And if we pass to 2060, so we use our strategy, we can reach a situation in which most of the load is matched with mainly wind and solar. This means having almost 92% of renewable energy into the mix, and some residual of gas that is mainly used, as you can see, during the winter months, that because the solar radiation is lower in that period. Where to install all this amount of PV? 130 gigawatt can cover 0.4% of the Italian surface area. That means almost the area of the city of Rome. So it's not really so much. And here you can see how we can select different areas that can be used to install this power, and the PV potential of each of these areas, and what fraction of this PV potential we need to reach the goal. So this is something that seems to be feasible, but we need to change paradigm, in the sense that we need to pass from the distributed generation, in which there are many actors that are involved in the production of renewables like wind and solar, with different actors that manage the energy injected into the grid, to a different system in which we centralize solar and wind generation, using the same grid that is already available, and using the same managing of the TSO and DSO that we currently have, but introducing large and flexible PV and wind farm. If you want to have more information about our work, here is the paper that we recently published on Renewable Energy Journal. And before leaving, I just show you a funny drawing that my daughter made some years ago, depicting what is a renewable energy world. I think that is a hope for the future. Thank you.
Thank you, Christina, for sharing that with us. And with that, and of course, obviously, for your presentation as well. With that, we now come to the final presentation by Mathieu. Before we get into that presentation, I already sent everybody a message to the chat. Looking at the clock just now, we will extend the duration of the webinar so that we can actually get to the Q&A session, which I know everybody's looking forward to. So if you can, we very much appreciate you staying on a bit longer. And with that, I'd like to introduce to you Mathieu. Mathieu is Associate Professor, and he's also currently the head of the laboratory PMENT of the University of La Réunion, as well as a senior lecturer. And his main field of interests are energy metrology, and specifically, he's involved in research projects on low consumption buildings in tropical areas, and the integration of intermittent renewable energy in the energy grid. So I'm going to move the screen to Mathieu. Here we go.
Thank you very much, Arabella, for the introduction. I hope you can see my screen and hear me.
Mm-hmm.
Yeah, so hello everybody. I will give a short presentation about an application of the methodology previously detailed by Marc and also previously in the last presentation, and it's an application on the insular grid of Reunion Island. So first of all, let me introduce what is Reunion Island. So it's a small island in the middle of the Indian Ocean of Madagascar. The population is nearly 1 million inhabitants, and it's also a French overseas territory and also an outermost region of Europe. Reunion has an active volcano named Piton de la Fournaise. It's one of the most active volcano currently, and it is currently erupting. Due to the high relief of the island with a summit at 3,000 meters, almost all the population live on the coastal area. And the important relief combined with the trade winds produces also a large variety of microclimates. Now let's focus on the current electricity generation. On the map, you can see the transportation lines and the main production means. With an important number of consumers and a large variety of production means, the Reunion's grid is clearly not a microgrid. But it's not a connected grid with the mainland. This isolated grid is also more sensitive to abrupt variations such as failure or PV ramping events. You can see on the left, in 2018, the renewable accounting for 36% of the total generation, but the most important figure is the proportion of installed PV power. Indeed, penetration rate, the PV represented more than 20% of the electricity mix in 2018. So to deal with this important penetration rate, the local DSO already set up storages, and you can see them on the map. They are indicated by yellow discs. And furthermore, all the last utility scale PV plants were also equipped with storages. The local authorities and the DSO target a 100% renewable generation by 2030, but mainly by importing wood and bioethanol instead of coal and fuel. But this solution is not free in carbon emission. The first issue currently experienced is the limitation of the power produced by intermittent renewables. An example of this limitation is given in the figure. The white dashed line shows the limit, which corresponds to 32% of the total produced power in 2018. It's a regulatory limit. And as you can see, this threshold is reached for the 2 first days in the figure, and the DSO curtails the PV production in the middle of the day. So the DSO foresees to extend this limit up to 45% in the coming years by adding flexibility, such as storages. This technical problem will not be discussed today. We will focus on the issue and solution tackled by the project PEPS Réunion. This project involves the local authority, Réunion, the French Energy Agency, ADEME, the DSO, EDF, also Clean Power Research with Marc Perez, that spoke before, and the University at Albany. The main goal of the projects are how to mitigate the ramp events of the PV generation through spatial distribution of the PV system and the use of energy storage, and how to integrate more PV by taking into account the supply-demand balance using forecast, storages, and overbuilding PV capacity as seen before. Today, we will focus on this last point only and using the methodology exposed by Marc and also by Christina. And I think now you are very familiar with all the concepts they showed before. So the first step of the project was to develop an efficient model to predict the PV generation. To do so, we use satellite estimates of the solar radiance and also grid measurement as input for the other weather parameters. We built a spatial model with 23 distinct areas as shown on the map. These areas correspond to the 23 distribution networks of Réunion. The PV model is very, very simple with only one system of a reference for every area. And furthermore, we calibrated the model with real data provided by the DSO. Regarding the overall accuracy, we obtain a small bias and a squared error similar to the one given by the satellite estimates. The second step is the definition of scenario for the future PV penetration and of the sizing of the associated needs in terms of storage and oversizing of PV capacity. We define 12 scenarios based on the following assumptions. First one is substitute the PV generation for fossil fuels with 2 scenarios. The use of PV as base load power with 3 scenarios this time. Supply specific load such as cooling demand, and we supply this load only with PV. To produce diurnal trapezes, that is easy with PV because we follow the solar path. And finally, 100% PV penetration, as explained before by Marc. We use the methodology developed by Marc to find the optimal combination between storage and other building PV capacity. In our simulation, we assume that the storage is only lithium-ion batteries, and we also consider the evolution of storage and PV prices from now up to 2050. The prices for regions are clearly higher than the continental ones, and it's mainly due to the small size of the system here. Now, in this slide, there are details, it's a detailed overview of the 12 scenario. So on the top left, you can see the first one, P1, that is a 100% penetration, where the PV fully supplies load. The two second one, P2 and P3, correspond to fossil fuel substitution. P2 replaces only the diesel generator, mainly used to shape the peak demand, while P3 replaces all the fossil fuels means of production. Scenarios P4 and P6 permit to supply specific loads such as cooling demand, the tertiary sector, or vacuum. Scenario P7 and P9 on the bottom left correspond to base load generation with constant powers, respectively of 50, 100, and 200 megawatts. Scenario P10 and P11 set up diurnal trapezes. For P10, the plateau is fixed at 300 megawatts, and for P11, the generation follows the load between the morning ramp up and evening ramp down. And finally, scenario P12 proposes PV generation corresponding to the day-ahead forecast, exactly as shown before by Christina. And the day-ahead forecast were given by the French Weather Services Météo France, and we choose a PV capacity of 740 megawatt peak for the forecast because it corresponds exactly to the maximum PV penetration without any curtailment for the producers. In this slide, the aim is not to look in detail to the results of the optimization, but to highlight the importance of the to available PV capacity. In dashed line, you can see the LCOE obtained without oversizing, while in plain line, you can observe the effect of the oversizing strategy. The latter reduces significantly the cost of energy. With increasing PV penetration, oversizing the PV capacity is clearly a key point to achieve affordable supply for the consumer. This slide shows the result for the 12 scenarios. On the left side, the graph presents the sizing in terms of PV power and storage capacity. During the project, we observed that the evolution of the PV and storage prices have a negligible influence on the technical sizing. So the sizing will be almost the same for now up to 2050. The required additional PV capacity is directly linked to the level of PV penetration of each scenario. Obviously, the scenarios that follow the path of the sun, I mean the last 3 ones, P10 to P12, require less PV and storage capacity. For the others, the storage capacity corresponds to more or less half a day, that is the night period. On the left side, you can see the results in terms of LCOE, and this time the effect of the decrease of the PV and storage cost along the year is very significant. Whatever the scenario, high PV penetration will probably lower the cost of energy in the future. From the previous results, we tried to trace a route to achieve a high PV penetration from Reunion Island. The top left figure shows how we selected the most relevant scenarios to define this path. Indeed, the most interesting scenarios are the ones that exhibit the lowest LCOE while the PV penetration increases. Here, the investment amounts are computed for the year 2019, but similar patterns are observed using future costs. A first possible path to reach the 100% renewable generation by increasing only the PV capacity is proposed in the second figure. It's not the 100% PV generation, it's 100% renewable generation. This path reaches the goal defined by the local government, but this time without importing any wood or bioethanol. The first step corresponds to the scenario P12, a firm day-ahead PV forecast. It means a significant increase of the PV capacity and a relatively reduced investment in storage. The second step, expected for 2025, corresponds to scenario P11 with a diurnal trapeze that supplies the load during daytime only. And the last step in 2030 corresponds to scenario P3 with a complete substitution for fossil fuels. For these last steps, almost all the PV capacity already exists, and we need to purchase a large amount of storage capacity. Finally, the resulting PV penetration for this path is nearly 75%. Other paths could be investigated. Here is a proposition to go towards a 100 PV penetration in 2050 at the least cost. With this approach, we are able to define paths to increase the PV penetration while keeping the cost of energy affordable. Until 2035, this alternative path is almost the same as before, but the costs are spread. The investment is spread along the year. So thank you very much for your attention, and I look forward to your questions.
Thank you, Mathieu, for that last presentation. And we now head into the Q&A session. So everybody, you can still send in your questions through the chat box. And I know that many of you have already done that. I'm just quickly gonna turn back the screen. And the first question to start us off is a question to Marc, Christina, and Mathieu, so most everybody, because I think it touches upon everybody's work in a broader sense. One of our attendees, they are concerned, is paying for a overbuilding scenario actually realistic? So are people actually going to pay to overbuild? And then again, overbuilding, how feasible is it still in densely populated countries? And I think especially in Mathieu's example, in a country, in a island that's restricted in the area that you can use. So overbuilding, a contested notion. Please convince us otherwise. And yeah, you're free to go, Marc, if you want to go first, and then maybe Christina and Mathieu.
Sure. I could touch upon, right now the markets, the energy markets that we all rely upon, were designed around a paradigm where all you had in the early 20th century, where all you had were dispatchable resources, or at least baseload resources. A very different paradigm from zero marginal cost renewables that are highly intermittent on various timescales. So I think it probably would stand to reason that we could redesign the markets and that it would probably be more efficient, but the markets are just, an illusion. There's plenty of resource, clearly. Whether or not the money, the market is structured correctly to make overbuilding happen, I don't really think so, but PV is getting so cheap that it's happening anyways, for other reasons, because you can provide, as a system owner, if you overbuild your system, you can provide ancillary services now in the current market, voltage regulation, ramp rate control, this kind of stuff. And I know NextEra, for instance, are overbuilding their PV. It's a big developer in the United States and around the world by almost 2x in several cases currently. And First Solar is also overbuilding, I don't know, 20% or something like that, or at least they were when they were still doing development. So the concept is gaining traction, and I think people are doing it de facto just so they can provide ancillary services in the context of the existing market. So I think it's going to happen eventually just because it makes economic sense. But I think it would go much more smoothly if we were to reconsider the way in which the markets were structured. That's my response. I'll let the others take it.
Thank you, Christina.
Yes, I think that Marc explained perfectly what could be the situation, and so I agree totally with him. For what concerns the place where to install, we saw for Italy, for example, that is not so large surface with respect to the Italian country. So I think that it could be possible to put these solar also using areas that at the moment are not used for a particular objective. So I think that at least for Italy, this could be feasible.
And Mathieu, from your side?
Yeah, I think for the overbuilding, it's already a real situation. For instance, in Australia, the PV is so cheap for the very large scale PV plant. They overbuild the PV field, and the inverters are clearly sometimes half the size of the PV fields, because they already know that the DSO will not integrate all the PV production because of the variability. So I think it's already something that happened in some countries. And regarding the variable surface in Réunion, we have currently a potential of 500 gigas of PV only on the roof in Réunion. And if you want to achieve a 100% PV penetration, we need 4 gigas. So we have enough roof to do it. And we assume in our simulation using only half of the real surface of the roof. And also in our LCOE calculation, we assume cost for roof installation that are clearly higher than ground installation. It's why also we have LCO that are clearly higher than the ones proposed by Marc or Christina.
Thank you. We have a few questions for Tobias for the PV EV scenario, and they do revolve a lot around the notion of social acceptance, which Tobias has touched up on himself. So Tobias, one question, for example, came in that said, well, it's all nice and fun, but what if I urgently need to use my EV car at night, but it's busy charging and recharging my local grid? And then, so how can I be sure there is backup still left for me? And then another person asked, well, why would I discharge my EV battery to only then recharge it the next day or to have it recharged? So the social acceptance, what can you say for that?
Yeah, the social acceptance is very, very important. And well, we have to look at the energy system as a whole. And I think what's going to come in the future, near future, is this self-driving cars. And actually owning your own car is going to be less and less common. And if you have this carpooling with self-driving cars, it's going to be much easier to utilize this kind of vehicle-to-grid technologies when it's not your own car anymore. Then we can have this interaction between carpooling and the grid to a much better extent. But of course, this, what I think is the beautiful PV EV system is not going to be realizable ever. You're going to have these mixes of wind and hydropower and other types of energy storages. So there's going to be room for I mean, in your app, if you join this kind of system, you're perhaps going to have an app, and you can choose these days I want to have this much state of charge in my car. This is my minimum, and so on and so forth. So you as the owner of the car is going to be able to choose whatever, to what extent you're going to participate in this kind of system, for sure. Otherwise, it's never going to be socially acceptable. But what I want to stress with this study is that there is such a huge energy storage resource here that we should use to some extent, and not utilizing it to some extent would be a waste, basically.
Thank you very much. Vasilis, a question to you. You touched upon the environmental life cycle evaluation of solar systems, and there's a question, is this evaluation based on the warranty of a solar system? So, for example, the warranty that is given out on a module or a storage unit, or can we actually take into account the actual and therefore useful life of equipment for solar? Is that possible at all?
I'm not sure if actually the question is about the life expectancy of a system. If it is in the calculations that have as a functional unit the kilowatt hours or the energy produced, we assumed a life expectancy of 30 years with a degradation of I think 0.5% per year, since the system actually would degrade with time. And that is conservative, really, because now degradation, even for crystalline silicon, has been reduced to 0.35% and thin films to 0.2%. And new targets for photovoltaic development actually set life expectancies even longer than 30 years. And there is an active research and development on making actually better encapsulation and so on, and extend the life. I'm not sure if this was really the question about.
I think that's, yeah, that's pretty much what the question touched upon. And then it was followed up by a question, well, if we think about overbuilding and the lifetime and the lifespan and expectancy on solar, what about the end of the lifetime? What about end of lifetime measures? What about recycling? How can we account for that? And maybe Vasilis, that's also a question.
Right, that's a very important actually question, a very important issue. We didn't have time to go over that, but actually recycling, it makes a lot of sense if you recall the three basic pillars of sustainability. That is the cost, the affordability, the resource, the materials, and the environmental impact. Recycling helps in all those three dimensions. You get in actually materials back into the life with lower energy and lower cost, and you actually prevent potential negative impacts by some kind of uncontrolled disposal. It is unfortunately it has not acquired a lot of focus because we're talking about big actually volumes after 25 years, and I would see more calls for research on recycling. We have done some studies, and others have done studies on the commercial technologies, and recycling of most of the materials is feasible. There is an industry actually wide voluntary system in Europe. It's called PV cycle, but I think the target of this is only recycle 65% of the components. So we need to do more, and we need actually to have in some way regulated recycling in the United States, in China, in other parts of the world. It is an important sustainability issue. We should do more thinking about recycling at the end of the life. The industry does recycle materials that they are spent from defect modules and so on during manufacturing, but we don't do as much as we should in thinking about the end of life of big volumes of photovoltaics.
Thank you, Vasilis. We are getting close to the end of the hour, and I know that one of our speakers has to leave soon. So I would like to close with one final question that goes out to Tobias. And we got a lot of questions in, and we can share them with the speaker still. So there will be a chance to follow up for sure. So one last question is, in your scenario, what about energy demand conflicts? Could there be demanding opposing demands on the grid, let's say by a private user and then maybe a corporate user, and how can the system account for that?
Yeah, again, the presentation I made was this really extreme energy system where you have only PV and only EV. That's not going to happen in reality ever, but it shows you the possibilities and the challenges. So of course we want to design an energy system which is reliant and robust, that we have yeah, we should never run out of energy. But actually that's an interesting question. Would it be allowed for a car owner? I have an electric car myself. Would it be okay for me to actually not have enough range one particular hour, one particular day? I'm not using my car every day, so for me personally, that would be okay. But of course, this needs to be a personal choice. And I also would like to add that modern cars have big batteries and they have driving ranges of more than 600 kilometers if you look at the best cars today. So even, well, say they have a battery of 80 kilowatt hours or 100 kilowatt hours, and we utilize half of it for this vehicle to grid purpose, then you still have 300 kilometers of range left. So and on average, we drive 50 kilometers per day, so it shouldn't be a big problem.
Mm-hmm.
But of course, yeah, but of course it must be an acceptable system for everybody, for the grid operator, for the personal owner, or for the carpool owner. And again, what I want to show with this study is the conceptual visionary possibilities of this kind of system.
Mm-hmm. Okay, perfect. Thank you very much. Thank you to everybody for submitting your questions, and thank you for all the panelists for being there, for answering them for us. We are now going to come to the closing remarks of this webinar. And I know that many of you already asked us about it. There will be a recording of this webinar, and there will also be the presentations which will be available on the ISES homepage. Both of these things, the recording and the presentations, they will be available online in a few days. For our ISES members that are with us today, please remember you already have the unlimited access to all past ISES webinars and presentations in our membership area. So you can just go in there and browse back, I think, all the way to 2015 or maybe even 2012. So there's loads to cover there. And then also there is the opportunity for a certificate of participation. If anybody's interested in that, you can obtain that from us, and you can just simply send us an email to public.relations@ises.org if that is of interest to you. And a final note before we say goodbye is that ISES is putting on the ISES Solar World Congress 2021 this year, and it's going to be a virtual conference this year in October from the 25th to the 29th. And I think this Congress, again, will be an excellent opportunity and an excellent platform to dive deep into the discussions that we had today and to get all our questions answered, hopefully, and learn loads about new approaches taken. And I'm sure I'm going to see many of the speakers from today's webinar also in that Congress. Registration for Solar World Congress 2021 is going to open in July. And in the meantime, you can stay up to date on swc.org. That's the Congress homepage. Yeah, and with that, I'd like to give a chance for a few last words to the speakers. And I'm saying thank you and goodbye from my side. Okay, bye everyone.
Thank you very much to all.
Bye-bye.
Bye-bye.
Bye-bye. Thank you very much.
Bye-bye.
Bye-bye, everybody. Thank you.
Great meeting you. And let's all